All right, today we're talking about Chapter 4, Section 4, the properties of definite integrals, the additive property, average value, and the moving average. All right, so first things first, we'll talk about the additive property. All right, so the additive property is what it sounds like. Well, we add them. Okay, we add integrals. All right, so the theorem here. Let's go ahead and actually let's snip that and put it on the page. All right, one moment. Alrighty. Sorry about that. All right, so the additive property. What is the additive property? Well, if we have some integral um, from a to b, we know that there is a point between a to b. We'll call it c. Okay. Well, if we wanted to figure out the uh, the area under that point, we know that we can just say, well, it's the area from A to C and from the area from C to B. Now, this seems kind of redundant and kind of pointless because you could think, well, why would I put an arbitrary point in the middle like that? Well, we'll see why here in a moment. Okay, and this example kind of shows what we're talking about. Let me make sure that that's all we need. Yeah. Okay. So the reason why it's well, let's actually pull the graph in. That might help us to at least visualize this. Okay. All right. So um, the reason why it really helps us is because in this particular question, okay, this is just we're wanting to find the area under the graph of f from -4 to 5. Okay. Now the thing is, it's a function, right? But it's a piecewise function, so we're going to have to split this up into two separate functions. And the two functions are for all values that are less than 3. So if we're going to go from -4 to a +3, well, not even +3, but well, yeah. Bear with me. So from a -4 to a +3, we're going to have the function 9. And then for values that are from 3 to 5, we're going to have the function x squared. And we're going to add both of those functions using our additive integral theorem here. So the way we're going to set this up is we're just going to say, all right, so we're going to have the integral from -4 all right, we're struggling here a little bit. From -4 to +3, right? And one of the functions is going to be 9. Okay, so 9 and then dx because we are integrating here. And then we're going to add the area from 3 to 5. So the integral from 3 to 5, maybe I should just write these larger, I don't know. From 3 to 5 of x squared. Okay, and again, all I did was just simply look at these functions and integrate from there. Okay, well, the first one should be pretty easy, right? This turns into just simply a 9x, and then we're integrating from -4 to 3. I forgot this textbook does the other side too. Yeah. So I grew up, excuse me, I grew up integrating and just kind of looking like this, just putting half a bracket on there. I will say that I haven't really seen that notation much once I got into my profession, but I guess the textbooks change. Man, my stylus ain't doing too hot right now. Anyways, and then we have we're gonna add. Well, what is if we integrate x squared, it becomes x cubed. Why are we? Whatever. It becomes x cubed over 3, and we're integrating from 3 to 5. Alrighty. All right, so if we do this, then all we have to do is, well, we just have to integrate, okay? And plugging in these values, Let's do some calculator work here. We've got 27 minus 36. All right, one moment. I think I might have messed up a little bit on my calculator. Everything's good on the screen. All right, so we end up with a total area of 95 and 2/3. Okay. Now, of course, this is just a piecewise function, and piecewise functions obviously going to be broken up into two functions that we need to add. The next example is, I think it's a little out of place, especially considering. I mean, I guess it's not necessarily out of place for what we're doing in this course, but I think it's a little out of place because we don't actually have the necessary means so far to actually integrate this problem, and we are tasked with honestly just kind of piecing together some puzzles. All right, so I'm snipping this whole thing to show what I mean by that. Right. So in order to integrate this, it's an absolute value. We would have to do the integration by parts, all that thing that I was telling you about later on. And integration by parts is really where calculus 1 gets really tedious and really hard. Okay. But we're not covering that in this course. So we're going to have to kind of, I don't know, to me as an instructor, I try to put myself in the shoes of a student, and I feel like a problem like this, isn't necessarily as cut and dry as the previous problems. And there's a difference between trying to figure something out and then just having no idea, no tools on how to work things. And I feel like example 2 is one of those examples. And I feel like you might have some of these on your homework. And so here's the thought process behind them. Okay, so you will have an absolute value kind of problem on your homework. So I didn't mean say might, but um, and what we need to do is we need to figure out. Okay, so if we were to actually graph this, the graph would look like this. It would, because it's an absolute value. That means our values are going to be positive, and so it would look something like this. Okay. However, the problem here is that we are if we're looking for the area under the curve, then the shaded areas are just going to be, right here, and then of course all the way here. Okay. Now I say the problem there. That is what we're trying to find the shaded region of. That is the area under that curve that we are trying to find. Okay. But the absolute value kind of messes it up just a tad. So what we're going to have to do here is we're going to have to split this up into two functions. Right? And so looking at our function here, 1 minus x squared, right? Well, we know 1 minus x squared is a parabola, the x squared. Well, it's a negative, so it's a parabola pointing downward, and then the 1 down there, or the 1 right here rather, tells us that we are at the x-axis at 1. Okay, again, this is just simply a transformation of a function that we're used to. And this is what 1 minus x squared looks like. Right? So we're going to have to integrate. We're going to have to integrate from -1 to 1 of this function, 1 minus x squared, and we're going to have to add it to our function of the x squared minus 1. All right. So again, this is something that I don't. I just feel like it's misplaced in this section. Yes, there's an additive thing to it, but I just feel like it's one of those things that you don't really have the tools for it yet. But here we are. So, anyways, with that said, if we split this up into two functions, we can change this essentially from the function f of x equal to the absolute value of 1 minus x squared. We could change it from an absolute value into a piecewise function, okay? But again, the piecewise function is just basically what's going to be our absolute value function, because we need to figure out that area under the curve there. So with that said, once we reduce this to a piecewise function, it becomes the exact same as example one. I don't know. There's not going to be one of these on the final exam. You can expect it on your homework, but not on the final exam. And that's really all I got to say about that. I'm not very I don't like that example, but I didn't want to just plain old skip it. All right, so the next concept we have is the area of region bounded by two graphs. Right. Now this is also pretty intuitive. This is something I feel like you can kind of come up with on your own, but we'll still talk about it. I say come up on your own because I mean it's not a hard concept. So let's put this. Shoot. Let's try that again. All right. So in the first example and kind of the second example, we talked about what it would be like, if we added the areas under a curve to get a final, total sum of the area under a curve. Right. Next up, if we're talking about two graphs, all right, two graphs, and I want to find the area between the two graphs. Right. So we have, looking right here, we have just simply a horizontal. I'm sorry, not horizontal line. A Well, just a line, I guess. A line here. And if we were to get the area under this line from A to B, well, then it's just this shaded area here. Okay. Well, if I wanted to find the shaded area between these two lines, if I were to have, let's move this down a little bit. If I were to have, I'm just redrawing the same thing here, just without the shaded area. Okay. If I wanted to know what the area was in between the two lines there. Okay, and again, keep in mind that this would be a graph. We're just trying to find the area there. If I wanted to find the area between those 2 points, well, if we think about this logically, then it would be the area. Let's erase this. You know what? Let's just start that over. Let me redraw it real quick so I can do all my shading. And then we'll do this. Okay. Again, it's just an arbitrary. That's not even a function. Let's make it a little more functiony. There we go. All right. So the area under, let's make them red and blue. Okay. So the area under the red is going to be the shaded green, right? Okay. Well, the area under the blue is going to be this yellow area that I'm going to try and shade in under here. Okay. Well, if I wanted to find out what this shaded red is, okay, do you see how it makes sense that what I would do is I would take the area, I would take the green area, and then I would subtract the yellow area, right? Pretty much all this. And then that would get me the area but underneath that red line. And if that's too confusing and said too much, the more pure example is here. Okay, we have our shaded area, and in order to get the shaded area between the two lines, then we just simply subtract A1 from A2. Okay, and of course that leads us into our theorem here. Let f and g be continuous functions with f of g being greater than f of x being greater than g of x, and all it basically says is, well, I mean, the function is above it, right? You're not going to be subtracting the area of this from the blue. Then the area of the region between the two curves from x equals a to x equals b. Again, that just means down here, x equals a is some arbitrary x equals b is some arbitrary x, and we just subtract the functions. Okay. However, right here it reads, sometimes we need to find where f and g intersect, as illustrated in the following example. So sometimes you could, like, well, for our theorem here, if we were to find the area between A and B, we can just say from here to here. Okay. But if we wanted to find out exactly where the points intersect, looking at our example over here, all right, if we wanted to have our A's and B's be exactly where the graphs intersect, well, that's the 2 points that we have to find. Right? Well, how do we find the intersection? Well, I'm glad you asked. Because this is one of those things that, like a lot of this course, is a concept that you may have learned earlier, but it's also a concept that you just kind of put on the back burner and then forgot. Okay. So first of all, let me see if I can graph this, or take this graph, steal the graph. Alright, so example 3 reads, find the area of the region bounded by the graph of f of x equal to 2x plus 1 and g of x equal to x squared plus 1. Right. So in order to do this, what we need to do is we need to find out where they intersect, okay? Because we're trying to find the area of region bounded by the graphs. So the arbitrary bounding there is where they intersect. Well, how do we find out where they intersect? Well, we have to figure out where they're equal to each other, right? Because think about it. Let's get our laser out here. So if we have, our blue line is 2x plus 1 and our pink line is x squared plus 1, well, we have to figure out where they intersect. And in order to figure out where they intersect, it obviously makes sense. They intersect where they're equal. Okay, so all we're going to do here is just equate the two functions. So we're just going to say 2x plus 1 is equal to x squared plus 1. And in order to do that, I'm going to have to combine them and use our zero product principle. So let's go ahead and let's move everything to the right so we can have a positive x squared. So we're going to end up with a 0 is equal to x squared and then minus 2x, and the 1's cancel. So this means that we can factor an x out. So we're going to have, let's just go ahead and move everything to the left now. So we're going to have an x. We factor out, we get an x minus 2, minus 2, and that's equal to 0. So therefore, our points of intersection are going to be at x equals 0 and at x is equal to 2. Okay. So again, just equate them to one another, and that's where they intersect. And of course, we see on the graph, that is indeed where they intersect at 0 and at 2. So what we're going to do is we're going to take the upper function, which is the 2x plus 1. Right? So we're going back to our definition. F of x has to be greater than g of x, so we're going to be taking the function that is greater, higher up on the y-axis there, and we're going to be subtracting the g of x from it. So what we're going to do is we're going to take the integral from 0 to 2, and we're going to have one function be 2x minus 1, and then subtract the other function being x squared plus 1. So we're going to set up this equation like this. We're going to say the integral from 0 to 2, okay, and then we're going to say of 2x plus 1, x plus 1, and then we're going to subtract x squared plus 1. So minus x, let's put it in parentheses as well, minus x squared plus 1, and then dx. Right. And let's go ahead and snip this, put it on the next page. That's actually, we can do one more line. Let me move this out of the way though. Okay, so we can say the integral from 0 to 2, and combining this fraction, looks like we can, or not fraction, but these two terms, looks like we can say the 1's cancel, so we're going to end up with a 2x minus x squared. So 2x minus x squared dx. Right? Now we can snip this and put on the next page. Continue from here. All right, so if we integrate this, well, the 2x can turn into 2, so it's going to just simply be x squared and then minus the x squared goes up to a 3, and then divide by 3, so x cubed over 3 dx, not dx, sorry, 0 to 2, got ahead of myself. And then if we integrate this, we end up with, luckily I don't have to worry about the 0 there, do I? So it's just 2 squared, which is 4, 8 thirds, so 4 minus 8 thirds, which is 4 thirds. So that area is 4 thirds. Okay. So that's how we find the area between two lines, is we subtract one area from the other. All right, now let's use a real world example here. I do like that this class has a lot of real world examples. I know you don't, but I like it. Alrighty, so example 4. So a college student develops an engine that is believed to meet all state standards for emission control. The new engine's rate of emission is given by E of t is equal to 2t squared, where E of t is the emissions in billions of particulates per year. At time t in years. Okay, that's one sentence, Sherman. At time t in years. So suppose the emission rate of a conventional engine is given by C of t is equal to 9 plus t squared. The graph of both curves is shown at the right. Okay, so we're trying to figure out A, at what point in time will the emissions rate be the same? Well, we want to figure out when they're going to be the same. That's just going to be where they're equal to one another. So A is a college algebra, not even a college algebra. It's like an intro to college algebra problem. We just equate them. So we're going to say 2t squared is equal to 9 plus t squared. Looks awful. T squared. There we go. All right, so it looks like it's just going to be, we've got t squared. We subtract. Okay, so let's just go and do it the long way. I'm scared to mess this one up. 9, and then it's going to be a minus t squared. Okay. So I have a 9 minus t squared, and so I'm seeing a difference of squares, but I'm going to just go ahead. I know it's kind of weird, but we know there's a difference of squares, and I could say 3 plus t, 3 minus t. All right, there's nothing wrong with that, but I know that many people, including myself, like to have the variable be positive. So I'm going to go ahead and add t squared to both sides, and I'm going to subtract 9 for both sides. Okay, so I'm going to end up with a t squared minus 9 is equal to 0. Now that makes it the difference of squares that I'm used to, t plus 3 and then t minus 3 is equal to 0. So therefore I've got t is equal to plus or minus 3. Now real quickly, I'm going to go ahead and look at this real fast because some of you might not want to change it to having a positive t. Well, again, this is still a difference of squares, right? This would just end up being 3 plus t, 3 minus t is equal to 0, and we're still going to end up with a t is equal to plus or minus 3. So we're not changing the value of anything at all. I just like having it on the left side. I'm sorry, I do. And I think many of you do as well. But yeah, I just wanted to go back and show you that, no, I didn't really change the value of anything. I just changed it the way I like them. Anyways, so going back to the problem, at what point in times will the emission rates be the same? Well, they're going to be the same at, are we in years? T is years, right? Yeah, t years, okay? So we have t is equal to plus or minus 3. Well, I don't know about you guys, but I can't go back in time, okay? So that tells us right away that we can pretty much disregard the negative t. Okay, so I don't really care about the negative 3. So the only time that these two graphs are going to intersect. Now, of course, if I were to graph this out, it would look something like this. That's horrible, but it would indeed be intersecting at positive and negative 3. But since we're talking about an emissions test, our domain, the thing that we talked about plenty of times before in your previous courses, our domain is restricted to greater than or equal to 0 because, well, that's how we perceive time. So that's why we disregard the negative 3. Um, anyways, that actually concludes A. So at 3 years, they are going to be the same. And then B, what reduction in emissions results with the student's engine up to the time found in Part A? Okay, well, we have our interval. Our interval is from 0 to 3, and so all we have to do is set up the integral. Did I say integral or interval? We have our interval, and we need to set up our integral. Okay, so we're going to say from 0 to 3, and CFT is 9 plus t squared, and they're going to subtract 2t squared dt. That right? All right, good. Make sure I wrote dx there. All right, and let's snip this and put it on the next page. Okay. So it looks like we can cancel out at least one of the t squareds. So from 0 to 3, I've got 9, and the plus t squared and minus 2t squared. Well, that ends up being a minus t squared. So minus t squared dt. All right, so that's going to be equal to, simply, we just integrate each term, so it's going to be 9t minus t cubed over 3 from 0 to 3. And again, that 0 is very convenient because we don't necessarily have to do the second part of the integral. So we've got 27 minus 27 divided by 3, so 9, 27, so 18. So that's equal to 18. All right, so 18 what? 18 particulates per billion, I think was the word. Yeah, billion. Oh, I said it backwards. In billions of particulates. Okay, so the reductions in emissions is 18 billions of particulates per year. Guys, I don't know how many a billion particulate is, but then there's the number. All right, so next up we're going to be talking about the area. Well, we've talked about areas actually. The areas of continuous functions. The area is the whole idea of the integral. All right, so continuous functions. So all this is all. Yes, it's interesting, but I don't feel like for you it will be that interesting. Instead, you really will care about the meat of the lecture, and that's our definition here. Alrighty, so the average value of a continuous function for f, a continuous function over the interval a, b, and again, that's basically any function you're going to be dealing with, at least in this particular course, right? If we are continuous over the interval from a to b, the average value, right, the average value that we're going to denote as yav, the average value, is given by, well, really, it just looks like the integral, right, from a to b. Nothing changes here. The only thing we have to add in here is we're going to say 1 divided by the difference of b and a, and that's it. There's nothing more to it. We're just taking the integral from our interval and we're multiplying it by 1 over b minus a. So let's go ahead and put that into practice. And honestly, I think I would have snipped this whole thing. There's no point in me going through all that. It's not very long. So if we want to find the average value, so the average value is, let's see, we know what average value is, but we're talking about the average in, I don't know how to word this. So in the past, when we've talked about like average speeds and average velocities, things like that, we typically dealt with something going, 30 miles per hour. I don't know. We would typically say something like somebody went 600 miles in 6 hours. Okay, and then we'd have to figure out the average value from there. Okay, well that's obviously, ooh, maybe we didn't travel at 100 miles per hour. All right, you know what? Fine, we travel 100 miles per hour. Um, and that's how we typically figured out averages in our previous courses, right? But that was just a nice steady. That was just a nice steady uh, equation. It wasn't hard. We basically said it was 100 t, and then whatever the t is the hours, and so we traveled that fast. Now we're doing things where we actually have more of a direct change. Okay, so again, keep in mind in differential calculus we talked about rate of change. In integral calculus we're talking about the area under a curve. Okay, well that area under a curve will also change depending on depending on the curve obviously. All right, and so what we're trying to do is we're trying to find the average value. What is the average area essentially? Okay, so that's the concept behind the average value of a continuous function. So as I mentioned, the way we set this up is super duper easy. All you basically do is integrate like you would, except now you're going to multiply it by 1 divided by b minus a. Well, b here is 2, a is 0, so you're going to multiply this by 1/2. So you're going to take your integral, you're going to integrate, you're going to solve, right? So x cubed over 3, and then minus the 0, it doesn't really matter. Well, it's going to be 8/3, so you're going to say 8/3 times 1/2, or in other words, 4/3. Right, so when you need to find the average value of a continuous function, again, it's the exact same procedure that you're used to, except now we're just multiplying it by something. That's the average value. Okay. Now let's actually do an example that's a little bit tougher. Alrighty, so this function is rather ridiculous, but it is what it is. So Rico is standing in a very long line waiting to enter an arena to attend a concert. His speed in feet per minute, t minutes after getting in line, is given by this function here. Okay, so this is his speed. Obviously, checking out the function, it looks like as he moves along, the speed goes up, but then when he gets kind of to the door, I guess the speed goes down. So from 5 minutes after getting in line to 25 minutes after doing so, what is Rico's average speed? Okay, so we need to figure out what his average speed is from 5 minutes to 25 minutes. And of course, we see the shaded area here from 5 minutes to 25 minutes. We want to know what the average speed is. Okay, so in order to figure out the average speed, we're going to have to do some integrating. And so let's go ahead and figure this out. So we know that we're going from 5 minutes to 25 minutes. So my b is 25 minutes, my a is 5 minutes. So the very first part of my integral, I'm going to write 1 over 25 minus 5, or 20. Okay, 20. And then my integral is going to be from 5 to 25 feet. 25 feet. I don't, whatever. I'm not sure if this is going to fit nice and neatly, but I'll try it. And if it doesn't, no big deal. I'll just copy it. All right, so we've got from negative 100 over 200t cubed plus 3 over 20t squared minus 3/8 t plus 60, and then dt. Well, let's put a d there first. Dt. Alrighty. So yeah, let's just do it. So we're going to have 1 over 20, and if we integrate this, this is going to be, we can integrate each individual term. So it's going to be t to the fourth, and that 4 goes in the bottom, so we're going to have a negative 1 over the 4 goes in the bottom, so 800 t to the fourth plus the 3 divided by 3, so 3 goes in the bottom. Oh, yeah. So we can just cancel that out. It's pretty easy, 60. So we're going to put a 3. No, the 3's cancel. So t cubed over 20 and minus 6. So 3 over 16 t squared and then plus 60 t. And we are evaluating from 25, or from 5 to 25. And let me see, does that make all sense? Yeah, okay. Well, I'm going to actually, I'm not going to evaluate this. I will snip what we have here, pray that it's correct, and do it from the text. I know, I'm pretty sure it's correct. So we've got right, 1 over 800, t over 20, 3 over 16. Okay, so everything's good. Didn't mess up, that's good. It's always embarrassing when I do. All right, so once we evaluate this, obviously the first time around we plug in a 25 and then subtracted whenever we do a 5. So we end up with 68 and 3/4 feet per minute. Let's see, was there actually a B part? Yeah, there kind of was. Okay, so we wanted to find the average speed. The average speed was 68 and 3/4, whenever this leaves. All right, and we want to know how far does he move over that time. Okay, well, from 5 minutes to 25 minutes, that's 20 minutes, right? So obviously we're just going to multiply 20 times his average speed, which means he moved 1,375 feet. So the last part, just pretty simple. All right, so next up is the moving average. This section can be skipped without loss of continuity. Well, we're not going to skip that. I didn't actually double check, but maybe this is actually skipped in the homework. I don't actually remember a problem like this. Oh well, if it's skipped, it's skipped. If it's not, it's not. But we're going to go over it regardless. Yeah, I actually don't think it is in the homework. I don't know. Alrighty, so moving average. We've talked about we just got done with the average value. Okay, the average value of some sort of function. The average value over a time interval of a function, and we're dealing with harder equations than what we're used to, right? Like I said, what we're used to, we've seen the move miles per hour stuff, right? Um, Same thing kind of here. So we're talking about the moving average. Well, the moving average of anything typically is just you basically just sum up all of the you sum up all the points and then you divide by how many points there are, right? Just a moving average. Well, the way we do a moving average for a function here in calculus, all right, is again kind of the same. I won't say the same concept, but we still use our integral. We still evaluate from x, But then what we do is we actually add. Yeah, we definitely don't do this on a homework actually. Um, and then we actually add um, the point to the upper limit. Okay. Now again, this is let's see. Do an example here. Right. And real quickly, what's the point of having the moving average? Well, it makes things a lot easier to see. So if anybody is, I don't know if anybody is, but if anybody has actually dealt with stocks or something like that, um, well, there's a lot of noise in the stock market. But if you use a moving average, it helps to clear up the noise, and you can actually see where are we going, what the moving average is, are we trending up, are we trending down, and things like that. And that's what we're doing here as well. I think I should put this on a new page actually. Alrighty. Well, I messed that up. Okay, so I probably shouldn't even be going over this, but I will. All right, so we have the weekly revenue, which is R of X, and thousands of dollars of true X of trucks rentals, X weeks since the start of the year is given by our function here. Okay, so we're going to have X between 0 and 10, and of course X is in weeks, so we're talking about just 10 weeks. So we want to find the moving average after a 3-week interval. So in order to do such thing, we know that my interval here is 3, so we make 3 be our upper limit. And then of course since that's our upper limit, you do the upper limit minus the lower limit to get the denominator of our fraction. And again, that's here. And then we just integrate. And again, I say just integrate. There's my hand waving. But we just integrate the function, and so we see our moving average is simply 16.91. And this is why it's not on the homework, is because doing all this tediously for each moving average is, well, it's tedious. But yeah, I guess I got to go over it, even though it's not useful. Um, believe that does cover it. Covers everything in the section, and I'll go ahead and double check to make sure on the homework that's not on there, but I'm pretty sure it's not. Anyways, that concludes today's lecture.